So this starts our nitrogen management part of the day. So Yeukai Katanda is a soil scientist specializing in soil fertility and soil health. She holds an MSc in soil science from the University of Manitoba and a PhD from Trent University. She has a range of soil and cover crop research experience across Canada and is currently actively involved in the assessment of cover crop mixtures for annual forage and silage crops in Western Newfoundland. Yeukai currently works at the Grenfell campus as the research coordinator for the Newfoundland and Labrador Living Lab project. So with that, I will let you take it away.
All right. Hi, everyone. I think Rosalie just introduced me, so I won't say too much about myself. Thank you all for being here. I was asked to talk a little bit about some of the work that we're doing here at Grenfell campus in Newfoundland and Labrador. We're working with enhanced fertilizers that have ureas and nitrification inhibitors. So today I'm just gonna talk a little bit about that, as well as giving a brief background to what nitrogen use efficiency is and what okay, there we go. I can't move my slides. Okay, it worked now. Right. So yeah, I'm going to talk a little bit about nitrogen use efficiency and what are its implications for agriculture, particularly in the Atlantic provinces. I may not have, enough knowledge required to talk in detail about Atlantic provinces, but I'm hoping that the discussion after this presentation will help us all kind of dig deeper into how we can improve nitrogen use efficiency if it's a concern for all of us. I'll also talk about the enhanced fertilizers, what they are, the mechanisms of their action, and how effective they are based on other studies. And I'll also talk about the project that we have done here at Grenfell campus that involve the enhanced use fertilizers. Then I'll give a little bit of what I think are my recommendations looking into the future about whether to adopt these slow release fertilizers or not. So since this session is hosted by the OFCA program, I thought the context has also to sort of address that idea of can we use nitrogen use efficiency as a way to mitigate climate change impacts. And as we all know, agriculture contributes about 8% of the greenhouse gas emissions from all Canadian economic sectors. Of course, you can't compare it with the energy sector, but 8% is what agriculture contributes. And about half of that comes from agricultural soils if we take out manure management and fermentation from livestock. For that, for the greenhouse gases that are produced from agriculture, most of it is carbon dioxide, followed by methane. A little bit is nitrous oxide, but as you may well know already, nitrous oxide has a very high carbon dioxide equivalence, which is like almost 300 times more powerful as a greenhouse gas than carbon dioxide. So it is of concern. And 75% of the nitrous oxide emissions come from agriculture. So nitrogen fertilizers being a big part of that. Now, coming to the Atlantic provinces, this is some of the data that I found on the Environment Canada or Statistics Canada website about the current levels of what are the emissions from the different provinces based on economic sectors. And for agriculture, about 25% of the emissions from Nova Scotia can be attributed to cropping systems where livestock or manure management is not involved. The same applies for Newfoundland and Labrador. It's about 25% of that. It's a little bit different for PI, where you have almost 50% coming from croplands where you're not even using manure or livestock are involved. And the same applies for New Brunswick. I included this just to show how different regions are going to have different objectives and different issues to address because of the differences in the cropping systems and obviously the management practices that are involved in those cropping systems. So Rosalie mentioned when she introduced this session earlier this morning about the Canadian climate plan led by the federal government. So there's a lot there. I don't work for the federal government. I don't intend to talk about this, but I just wanted to show that there's a lot going on, and we hear a lot about how everyone can contribute to climate change mitigation. I also got this, and I thought it was really interesting because it's a recent response from the Fertilizer Canada, which is a big partner to the agriculture industry in Canada, responding to the report by the federal government, and obviously agreeing that yes, we all need to do something, but there's obviously a lot of other things that need to be taken into account. Not just let's reduce greenhouse gas emissions, but there's also the farmer's bottom line. So there are so many objectives that need to be taken into account when we talk about these things. And I say all this because as a scientist, I always want to remind myself that it's not just about the data and the issues that I'm interested in, but it's also looking at the fuller picture of what matters to all the stakeholders. Now, I'm going to talk about nitrogen use efficiency, but before I talk about that, maybe just a refresher on what the soil nitrogen cycle is. So nitrogen enters the soil system from different through different pathways. So atmospheric nitrogen can enter the soil system through the biological nitrogen fixation, which is a symbiotic relationship between legumes and some bacterium, which convert the nitrogen gas into ammonium. The ammonium then is converted to nitrate. Nitrogen also enters agricultural systems through the application of either organic or inorganic fertilizers. When nitrogen comes in as organic forms, it has to be broken down through biological activity into the ammonium and nitrate, because these are the two forms that plants can actually use. Most soluble fertilizers are applied with either ammonium or nitrate, or they can be in the form of urea, which is a very popular and very common fertilizer. And we're going to talk a lot about urea today because we're talking about urease inhibitors today. Now, once the ammonium and the nitrate are in the soil, they're also susceptible to a lot of pathways, including plant uptake, so plants can use those. Or if they are not taken up and they're just available in the soil, they're also susceptible to losses through like leaching, through runoff, or some of the ammonium can be bound by clay, which makes it safe, but only for a little while. When conditions are conducive, that ammonium can be converted into ammonia gas and can be lost into the environment, or it can also be converted to nitrate. Nitrate, on the other hand, if there's an excess amount of it and conditions are conducive for it to be lost, can be lost through leaching. On the other hand, under low oxygen conditions, nitrate can be denitrified and be converted to nitrous oxide, which is the greenhouse gas that I was talking about before. Now, just one thing to keep in mind is that not only soluble fertilizers are responsible for environmental risks that we see from nitrate or ammonia, but even the organic material, the organic nitrogen, also needs to be managed efficiently to avoid these lost pathways. Now, talking about nitrogen use efficiency, the idea is to promote the amount of nitrogen that is taken up by the plant, as opposed to the amount that is just lying around in the soil waiting for other pathways, such as being converted to nitrous oxide or being lost into the environment and becoming a pollutant for some water sources. So broadly defining nitrogen use efficiency, and this is something that you'll see in a lot of policy documents or high-level conversations. When people talk about nitrogen use efficiency, it's usually just how much fertilizer or how much nitrogen was introduced to a system, as opposed to how much was harvested in the product. And that is the broadest definition that you will find. And usually when you look at government documents, unless if it's a scientific publication, usually it's just that broad definition. And I saw this and I thought it was really interesting. Broadly speaking, Canada is doing really well because on average, fertilizer use efficiency or nitrogen use efficiency is expected to be around 50%. But according to this, Canada is on a very good trajectory here, an increase in the nitrogen use efficiency. So you see here from 2011 to 2017, nitrogen use efficiency is between 66 and 78%, which is pretty good. Now, there are a lot of indices that when you want now to either assess a fertilizer for its efficiency or to look at the agronomic performance of a BMP or a combination of BMPs, you would look at those different efficiency indices. Not all of them are useful for all stakeholders. For instance, a scientist will look at physiological efficiency if they are maybe looking at breeding new varieties of crops, because it means different from uptake efficiency. Now, I really don't want to get too technical because I realize that the audience here is not all technical, but all these efficiency indices are interlinked because they all depend on how much fertilizer or how much nutrient is available. So if we talk of uptake efficiency, we're usually talking about how much fertilizer did we apply and how much of it was taken up by the plant. This can be easily measured. So usually it's based on the above ground biomass because that's what we can actually collect. So if you collect the above ground biomass, measure the amount of nitrogen in that, and then compare that with the fertilizer that was applied. Utilization efficiency, on the other hand, is how much of that applied fertilizer was converted into biomass. Was converted into biomass. So that's a little bit different from uptake because this is like what was taken up, but for utilization, you're not talking about how much of it was actually converted into biomass. Agronomic efficiency is a little different from utilization efficiency because this is, you're now focusing more on how much of the applied fertilizer was converted into a harvestable product. So how much did it cost me to buy my nitrogen? How much of that was converted into a product that can give me cash back? That's what you'll be talking about. Partial factor productivity. This one is really broad because it doesn't account for just the nitrogen that was applied, but it just takes into account what was the rate at which I grew my corn or whatever crop. How much yield did I get? So it includes all the other sources of nitrogen that are in the soil. In other words, if you're a scientist, for partial factor productivity, you don't even need to have a zero control to determine how much yield you would have gotten without the nitrogen. That is what we call the control. And then the marginal return is just an economic indicator, which says, for the cost of my nitrogen, how much value did I get back? I'm not an economist, so I'm not going to get into details about that. Okay, so why does it matter? Why does nitrogen use efficiency matter? Depending on the objectives or depending on what the issues are, nitrogen use efficiency is important for determining whether a new practice, for instance, is worth it. So if, for instance, you're trying a new nitrogen source, or if you're trying to integrate your nutrition, say maybe introducing some organic sources, so you can see whether there's an improvement in the productivity that you're getting or the value you're getting from your fertilizer investment. So in some cases, it has been suggested that high nitrogen use efficiency is highly correlated to higher productivity. And also, because high nitrogen use efficiency, particularly if you're talking about uptake efficiency, also means that a lot of the nitrogen that you applied ended up in the crop, which means that the rest just remained in the soil. So if a lot of it was in the crop, it means you have less that is exposed to environmental losses. And so on the negative end, like I just said, excess nitrogen is vulnerable to losses. So you could lose that to leaching, surface runoff, erosion, or denitrification. Remember that nitrogen cycle that I just described before. So the nitrogen is not going to just sit there and wait for the next season. It's going to be vulnerable to other losses, which is not desirable. So now, how do we improve nitrogen use efficiency? There are a lot of solutions or proposed solutions to this. Not all of them are just to do with fertilizer management. Of course, there's a lot that goes into crop production or agriculture. And nitrogen use efficiency can be improved when it comes particularly to fertilizer management by employing the 4R principle. I think we must have all heard about this before, because it's a very popular model that was adopted by the Fertilizer Association, International Fertilizer Association, where you're looking at using the right source at the right time, at the right rate, and the right place, preferably all four together. But that is almost difficult to do sometimes, because you would need to account for a lot of other factors that go into determining what that right source would be for that time, or that application method, or what rate you have to apply, because all of these four are affected differently by environmental variables such as climate or soil. But these are the four key aspects of improved nitrogen use efficiency. Let's keep something. Okay, there we go. Okay, so now going into one of the aspects of the 4R principle, which is the source, the right source. Talking about enhanced efficiency fertilizers is not me suggesting that these are the right source, because there's no one-size-fits-all solution to the issues of nitrogen use efficiency. But the enhanced efficiency fertilizers have been proposed as one of the better solutions to reducing or minimizing losses of nitrogen when it's applied to soil. So there are different types of enhanced fertilizers. They can be polymer coated, or they can be stabilized using inhibitors. Polymer coated fertilizers, there are a lot of them on the market, like the ones that I have listed here. The most popular one is the environmentally smart nitrogen. I recently heard that what's the name of the supplier in Nova Scotia is now selling pure yield instead of ESN. So I'm looking forward to learning more about pure yield, but I already know about ESN. I don't know anything about polyon or NutriCort, but they are all based on the same concept of having a polymer surrounding the urea, for instance. And this is the mechanism through which these polymer coated fertilizers work. So at first, the fertilizer granule has to be penetrated by water, and the fertilizer inside dissolves. That's where you have that lag phase here. Once the fertilizer dissolves, pressure builds up, and then the fertilizer nitrogen starts diffusing out of the granule. And then eventually, when there's enough pressure build up, the granule will then erupt, and then you have the final, which is the decay. And then you have the final release. So ideally, that's how polymer coated fertilizers are supposed to work, but sometimes it doesn't work like that, because their mechanism relies a lot on soil conditions as well as soil moisture and temperature. So sometimes if there's anything wrong with some of the granules, you will have this failure pattern happening. In that case, it is no different from just applying urea. Now, the effectiveness of a polymer-coated fertilizer will depend on the proportion of the granules that will follow the nice sigmoidal pattern or the ones that fail. Okay. Now, onto inhibitors. There are two types of inhibitors that I'll talk about today. There's a group called urease inhibitors and a group called nitrification inhibitors. These are some of the examples of the ones that are on the market. They have been tested under controlled conditions, and there's a lot of research that has also been done. Field research that has also been done with most of these products. Now, how do they work? This here is a diagram just showing the pathway of urea when it's applied to soil, is converted to ammonium through the action of urease enzymes. Now, when you add urease inhibitors, they slow down or they will disrupt this process of hydrolysis of urea to form ammonium, causing a delay in the rate at which the ammonium becomes available in soil solution. On the other hand, nitrification inhibitors apply on the next stage, which is the conversion of ammonium to nitrate. This is where nitrification inhibitors come into play. So if a fertilizer is applied and it already has ammonium in it, then nitrification inhibitors would be more effective to be applied at that stage, because then they will be useful. If a fertilizer is being applied and it's only urea, maybe urease inhibitors will be more effective. But we'll talk about how these different inhibitors can work differently under different circumstances. This is just one diagram that I thought would be interesting for people to understand the concept of, or the mechanism of inhibition. So enzymes are very specific to the product that they work on or that they break down. So in the case of the urease enzyme, it fits well with urea. So the inhibitors mimic the shape of urea, and then they block that site, that active site, which is supposed to break down the urea for some time until natural degradation happens, and then the enzymes become active again. Okay, now when are inhibitors most effective, or when do you get the best value out of these ureas or nitrification inhibitors? Usually they are more effective, or you get more value for your money if you're expecting that losses will be high. So for instance, if you're applying a nitrate-based fertilizer and you have a tile-drained soil, so you know for sure that because of that system, that management system that you have, it would be beneficial to delay the conversion of ammonium to nitrate until the crop needs it. Sometimes also in poorly drained soils, it helps to have inhibitors, because you know that the susceptibility of nitrate to be converted to nitrous oxide is very high. Also, when for applications of fertilizers are practiced, it can be important to slow down the degradation or the hydrolysis of urea, because if fertilizers are being applied when the crop is not there, or if fertilizers are being applied before you go in to incorporate, then you may need to slow down that conversion. That also applies to broadcast fertilizer, and that's the best combination. Inhibitors with broadcast fertilizer applications, you can clearly see a response in there, because broadcast applications are generally inefficient because they expose the fertilizer to other environmental elements. Now, when do you get the least value from inhibitors? When everything is optimal and you already have an efficient system, it may not make sense to have that extra investment, or you may not see the kind of response that you would expect. It doesn't mean to say that there are no other benefits. Again, these these products don't just give one benefit. When we talk of nutrient use efficiency, we are not just talking about environmental benefits or production benefits, but it can be a combination of both or one or the other. So sometimes if the weather is great and soil conditions are not conducive for losses, you're not going to see any much response in terms of the yield, but there may be other benefits from having them. If nitrogen rates, going back to the 4R principle, if they are already excessive, or if this system is already inefficient in the sense of not practicing all the other, not adopting all the other best management practices, it may be difficult to see an increase in the efficiency of the fertilizers if it's the only thing that you're going to for a solution. And also side dress applications, as opposed to broadcasting, side dressing is already an efficient way of applying fertilizers. So sometimes you may not be able to see a response from inhibitors if you already have an efficient practice of applying the fertilizer. And then also the type of soil, a lot of research also confirms this. Coarse-textured soils, soils with high organic matter, or they may not respond as well to nitrification or urease inhibitors. Okay, so I found this one. Okay, how am I doing on time, Rosalie?
You have about 15 minutes left.
Okay, good. I found this one review paper that I thought was really interesting. It's brand new, so if anyone wants to read it, I have the reference here, and I also have a reference list at the end of my presentation. So this is the most recent I could find, and I thought it was really interesting because it really covers a lot of ground in terms of looking at different aspects of the adoption of inhibitors or enhanced fertilizers against like comparing nitrous oxide emissions, yields, and other parameters to all the factors that affect the effectiveness of these inhibitors. So I just chose to focus on just these three aspects. There are a lot of other things in the paper, you can read it. But here I want to just talk about the crop yields responses to, crop yield responses, and then the responses of ammonium volatilization, as well as nitrous oxide emissions. So when it comes to yields, so the red here are the urease inhibitors, the blue are the nitrification inhibitors, and the black are the combinations. So these are products with a combination of urease inhibitors and nitrogen inhibitors, or both. So anyways, what you can see here is, in general, for the most part, the averages for all these. So these numbers that you see here are the number of the sample sizes for these observations. So what you see here is that for the most part, the averages are showing an increase in crop yields when inhibitors are used. In a few cases, you have some of the results showing a decrease, because these bars are showing the range of the number of the average, of the data points that you got from these samples. For ammonium volatilization, very different story. When it comes to urease inhibitors, which are the red ones, there was a decrease in ammonium volatilization, but nitrification inhibitors tended to increase ammonium volatilization. On the other hand, nitrous oxide emissions were generally reduced when inhibitors were used. That's what this is showing here. This line is at 0, and in all cases, nitrification inhibitors reduced all inhibitor types reduced nitrous oxide emissions. Now, to quickly go over the CleanTech project that I talked about. So in 2019, I was hired here to coordinate this project, which was a collaborative project between Grenfell campus and the provincial government. And this study was set up at Pinsbrook Research Station here. And we had some of our students work on that project. I'll present some of their data here. The experimental design was just 5 crop sequences and 6 nitrogen sources. We had 3 by 4 square meter plots. Our soil was a sandy loam with this 3.8% organic matter. So this is just showing the 5 crops that we grew. So in 2019, we had silage corn in all the plots, and then we had, in 2020, we had silage corn, then in the other plots, faba beans, wheat, canola, or autumn peas mix. These are the 6 nitrogen sources that we tried. So we had no fertilizer control because we wanted to measure nitrogen use efficiency of these products. And we also had a full dose of urea at seeding, as well as a split application of urea compared to 3. So we tested 3 products in this study. So the first set of results I'll talk about from one of our students, Audrey Winter. I don't know if she's here, but I'm borrowing her data. So yeah, I just calculated yield responses from what she measured in 2020. And for 3 of those crop sequences, there were no significant differences among all of our treatments, actually. But the one thing I wanted to point out is that you see that the error bars here, they are really long, which shows that the level of variability that was there in our field, and also the effect of the background, like temperature, soil, moisture. So a lot goes on when you're doing a field experiment. What does that mean? It means we generally need more data from bigger fields than just the 3.4 square meter plots. So let's not get carried away with the results that we see here, but this is just a starting point just to show us a little bit of what is possible in our region at least. So I also calculated the recovery efficiency, which I described as the uptake efficiency before. So this is basically how much of the fertilizer nitrogen was taken up by the plant. How do you get that? I subtracted how much was taken up from the control. So in this case, for silage corn in 2019, about 26 kilograms of nitrogen was taken up from the control. So if you subtract that from all the nitrogen that was taken up in the treatments, then the rest must have been taken up from the fertilizer. But there's an assumption being made there because there's also other sources of nitrogen that may not have been accounted for. Like for instance, organic matter decomposition. But anyways, we didn't find any significant differences in the recovery efficiency. I don't know, like I have seen some people who calculate, these numbers, convert them into dollar values and see differences. But from a scientific perspective, not significantly different. I'd be curious to see what happens if we have a longer term experiment or if we have more experiments like this to test these products under different conditions. Same story with our silage corn in 2020. We didn't see any significant differences in the recovery efficiency. But for canola in 2020, we had significant differences. Canola did pretty well when the nitrogen was split applied with 92.4% efficiency, as opposed to the rest of the treatments. But even then, agrotane was the next, the other really impressive treatment here, but was not significantly different from the other 2 inhibitors or from urea. For wheat, same story as the corn, no significant differences there. Okay, now we had another student, his name was Irfan. He worked on looking at the effects of these stabilizers on gene expression in the soil. So he collected soil samples and measured the diversity of the genes that code for different processes in the nitrogen cycle. So this one is the gene that codes for that first step in the ammonification process. No differences there due to our treatments. But for this gene that is from bacteria, which also codes for the same step, there were significant reductions in the gene expression from the enhanced fertilizers. this shows that maybe there's something that we need to look a little bit more into in terms of the mechanisms through which these products are working in the soil, as opposed to what we actually see in terms of yield or nitrogen uptake. We're not seeing differences in yield, but something is happening in the soil. Yeah, same story with this next gene, which codes also for the process of nitrification. Significant reductions in the expression of that gene when enhanced fertilizers were used. And then this, I borrowed this from a fancy thesis, that's why it's a different theme. I didn't have the data to make the graph myself, but yeah, so here, no significant differences amongst the fertilized treatments, except all of them had a significant response in terms of the soil nitrate concentrations 15 days after fertilizer application. So this data, this soil was collected 15 days after fertilizer application. And there are no significant differences here. And then for ammonium, yeah, same story, significant responses from all the treatments. One significant result here is the higher amount of ammonium in the agrotane treated fertilizer as opposed to urea. Okay, so this is the same story, same story about gene expression. This is now the second step of the denitrification process, which is critical if you're looking at how much, like, what is the potential for denitrification to happen. So in the corn and wheat actually, where at least 100 kilograms of nitrogen were applied, we saw significant reductions in the expression of that gene. In the faba bean, we only applied 25 kilograms of nitrogen, showing that there is a difference there in the effectiveness of these stabilizers based on rate as well. So this is the same story for faba beans, no significant reductions in gene expression, because the rate was much lower, 25 kilograms per hectare, as opposed to corn and wheat, where at least 100 kilograms of nitrogen were applied. Okay, so this is the last one. It's just showing the nitrous oxide fluxes. So I'm not an expert in this stuff, and I don't know how to explain this, except I noticed that, so the peak of nitrogen fluxes happened around the same time for all treatments except urea, and this is for the corn. The one thing that was really glaring to me was that if you look at this, so these are the differences between urea and the other treatments compared to the control. But if you look at canola and wheat, the trends are a little bit different, and the responses of those different treatments are also different. Coming back to my point earlier about cropping systems, about the types of crops being also an important factor when you're looking at the effectiveness of these slow release fertilizers. Now, just to wrap up, I hope I'm not over time, but this is my last slide, I promise. So I guess we can discuss, but I think that before considering adopting these enhanced fertilizers, it's important to really determine what your current nitrogen use efficiency is and what other practices need to be taken into account so that they can be consolidated together with the enhanced fertilizers to make them more effective and worth the cost, the additional cost. So what are the aspects of the poor fertilizer management are being considered? So is the timing okay? Are you placing the fertilizer at the right place? Are you using optimal rates? And also, what is the product that you're choosing? Is it relevant to the type of crop, the soil, the climate that you are working under? And also, do you have any regional data that supports your decision to use that enhanced fertilizer? And is there any possibility that university research could be promoted or is already done that could support the decision that you're about to make in terms of adopting these fertilizers. Those are my thoughts with regards to using these fertilizers to address the issue of nitrogen use efficiency. I may have missed the mark, but I'm happy to discuss. So before I end, I would just like to thank our sponsors. So the project was funded by Agriculture and Agri-Food Canada under the Cleantech program. And we also partnered with the provincial government to do this work. And all the interns, including myself, were funded by NITAX. And we had a big team that worked really hard on all of this. I didn't do it alone. So thanks, if any of them are here, I'd like to thank all of them for the hard work. And thank you all for listening. That's it.
Fantastic. Thank you, Yeukai. If there are any questions, you can type them in the chat. Otherwise, we are going to have a coffee break in about 1 minute and then come back in about 10 minutes to hear from Harold Van Ness. Yeukai, would you be willing to put up that slide with the corn and the nitrous oxide emissions again? I just need to look at that for a little bit longer myself. It was like your third or fourth to last slide.
This one?
You stop screen sharing here.
Oh. Oh man. Okay, I thought I was sharing. There we go.
Yeah, that one.
Okay.
So do you have any thoughts on why there wasn't a nitrous oxide flux after that second split urea application?
I have no idea. I'm yet to look into that. So we are still processing this data. That's one thing I also didn't mention. That's why I wasn't able, I would have loved to look at whether there were other climate variables, because we did measure soil temperature, moisture, and we have the climate data also, sorry, the weather data also for this period. So I'm curious to know whether it had anything to do with, you know, the rainfall patterns or the temperature patterns at that time. But I'll be happy to discuss some more once we process this. We hope to be publishing this soon.
That sounds excellent. And I know Harold's going to be talking about climate data as part of his talk. So Dave has a comment in there in the chat that one of the observations from his work on enhanced efficiency fertilizers is that to realize nitrous oxide emission reductions, you actually need to reduce the nitrogen rate to reflect the increased efficiency of the nitrogen source. Mm-hmm. So we're going to pause on that excellent thought and go on a coffee break real quick. And then we'll come back in 9 minutes at 2:20 to hear from Harold Van Ness from Cornell. Harold, thank you so much for joining us. I'm going to introduce you and then I'll let you take it away.
Great.
So, Harold Van Ness is a professor of soil science and served as chair of the Soil and Crop Sciences Department and president of the Soil Science Society of America. He leads the Cornell Soil Health Initiative and was the lead developer of the Comprehensive Assessment of Soil Health framework, and has also co-authored the influential book, Building Soils for Better Crops, which, as an aside, is a total favorite of mine, Harold. He is also the lead developer of digital technology for crop nitrogen management, ADAPT, and licensed to YAR International, and spatially balanced designs for field experiment, available through ARM software. He teaches courses on soil and crop management and impact learning. So with that, Harold, thank you again for joining us, and please take it away.
Well, thank you so much. Can you hear me? Can you just confirm that you can hear me?
I can hear you great, and your slides.
Okay, great. I'm thank you for allowing me to present to you. I'm actually currently at another conference in Syracuse, New York, and I'm working off a single laptop, so I'm used to giving presentations with multiple monitors. So I hope it goes well, but I assume you can see my slides and we can proceed. So and I caught a tail end of the previous presentation, which was very interesting, and so I hope to add some context to that as well. So when I talk about multi-objective production environments, what I mean is that, you know, we're not necessarily only interested in outcomes like yield or even quality of yield, but we're also interested in soil health, water quality, reducing climate impacts, mitigating that, and so that does change the picture a little bit in terms of how we want to manage our crops and crop inputs. So Rosalie mentioned the book that I co-authored with Fred Magdov, and I just wanted to point that out in terms of that. Last year we came out with the 4th edition of this book, and as in the previous cases, the book can be accessed for free electronically as a PDF file. If you just Google the title of the book, you'll get there. We also do at Cornell University a lot of work on soil health, and we've had some collaborations in your area in Quebec and Nova Scotia, certainly, and I think in New Brunswick as well. And if you're interested in that, we also have these training manual that focuses on the CASH approach, a comprehensive assessment of soil health. So just some literature in case you're interested. But I especially wanted to point out that we have an update on building soils for better crops. Okay, so nitrogen, and that's obviously the focus, and I have to commend you since I'm in the United States. I have to commend my Canadian colleagues for it. It appears that there's more emphasis on nitrogen in Canada as it relates to climate impacts than there is in the U.S. In the U.S., it seems like we're mostly talking about carbon and methane, which is also important, but nitrogen, of course, is a big factor. And obviously, as you know, nitrogen has a number of concerns related to agronomic and economic issues. It's costly. Use efficiency is generally relatively low, and there's this issue with the high uncertainty and the sensitivity to climate change, especially as it relates to the impacts of weather. And then the environmental aspects being, multiple, which is really kind of makes it, something that's very worthy of study. So the energy component, the greenhouse gas component, of course, the water quality component, both in terms of groundwater and hypoxia and dead zones, and then the particulate formation in the air from ammonia. So lots and lots of interest, and that's why we need to put more attention to that. So just in case, and I don't have the Canadian numbers, but in the US, according to the Environmental Protection Agency, more than half of the agricultural impact on greenhouse gas emissions is associated with nitrous oxide, and most of that is what generally is referred to as agricultural soil management, which is really nitrogen application on fields. And in the US, that's about equivalent to twice the impact of the US aviation. So I always like to say, if one of the big airplane manufacturers said, we can reduce the impact of our planes by 30%, that would be a big news. And we can do that with nitrogen, but it's not as big news as maybe we'd like it to be. So I assume that you're all familiar with the 4 R's of nutrient management, and especially the industry is really on board with that, which is great. And it's the right source, right rate, right time, and right place. And it's a good concept, but you do have to ask yourself the question, what is right in this case? And I think with source and time and place, we know that source. It's and in fact, the previous speaker talked about that. The timing, typically close to when the crop takes it up, and the placement is, typically not service applied, or in many cases perfectly banded, and certainly in the case with manure also incorporated. But the right rate is always a very challenging question, because the rate actually depends on the other 3 R's, the source, time, and place, and is strongly impacted by weather conditions. And so that's why the rate remains really, the right rate is an elusive concept. So, and why is it so difficult to estimate the right rate? Well, because of all these processes that happen in the soil that impact the availability of nitrogen to a crop. You have many different sources. It can be synthetic nitrogen, it can be nitrogen from manure, it can be from fixation by legumes. It ends up in the soil being transformed, mineralized, or immobilized. And then it may end up in the nitrate form where it's subject to leaching losses, or it may go back out in gaseous form as dinitrogen or nitrous oxide. Ammonia, of course, is another big issue, especially when there's animals involved. But ultimately, you'd like to get as much as possible of that nitrogen into the crop. And the way to do that is to make sure that you apply at the right rate, but also, of course, at the right timing and placement, et cetera. So, but the availability of crop nitrogen is impacted by the production environment, like the soil types, the climate, et cetera, by management practices and weather conditions. And there's a lot of spatial and temporal variability, even within fields. So when we look at the right rate, and you look at some data, so this is from Iowa State University, where they have sets of nitrogen rate experiments that have been conducted. In this case, corn after corn and corn after soybean, and they do that year after year after year. And they have say 6 or 7 nitrogen rates, say 0, 40, 80, 120, etc. And then you do the curve fitting and then determine what the optimum N rate is. And then you get a graph like this. And then the question is, well, what is the right rate, right? There obviously isn't a single right rate. And this high variability, it's really from 0 in some cases to 250 or maybe even higher. So one approach might be to say, like, well, maybe the optimum rate should be somewhere between 150 and 175, because that's where in most of the cases that would be the optimum. But then in some years we will over fertilize, and in other years we will under fertilize. Now, it is clear that if you grow corn after soybean, you have a little bit of a credit, maybe 30 to 40 pounds per acre that comes out of that. But it's very difficult to say that there really is a right rate, even though many of the universities they promote a particular rate that's sort of that average. Now, one of the issues associated with nutrient management in general, but it especially applies to nitrogen, is risk. So risk is probability times cost. So if we look here at the nitrogen rate, and this is from the producer perspective, and we know that there's some uncertainty around the economic optimum nitrogen rate. We saw that in the previous slide. So given that uncertainty, if this is sort of the average, but there is that uncertainty, if the farmer under applies, then they have a risk of yield loss, and that's quite expensive, because losing yield is very costly. If you over apply nitrogen, you ended up wasting some money on fertilizer, but it's nothing compared to the risk of yield losses. So a farmer has an incentive to not go for the average, but actually when you do an economic calculation is to apply a little bit more than the average, maybe 30 to 40 pounds per acre or more, according to our research. Now, contrast that to the sort of societal impact, so the environmental risk. Well, the problem there is mostly with excessive rates, right? So as long as all the nitrogen ends up in the plant, or at least most of it, there's relatively little risk. But once you start to have excessive nitrogen rates, that's when the risk increases. That's when we see a lot of losses, either gaseous losses and the greenhouse gas impacts, or water quality impacts. So you can see that there's obviously some contrast in terms of the risk, and so what is really, in a way, the solution to that is to say, well, let's try to at least accurately and precisely predict what the economic optimum N rate is, so that we can reduce the risk to the grower, and if we can provide them with better information that allows them to better estimate the economic optimum N rate, then they don't have to deal with the uncertainty, and then they don't feel like they need to to increase their N rate to address this risk component. So, but still sort of recognizing that risk exists. And I think this is an important concept, and a lot of when I talk to people about programs to reduce nitrogen rate, I always bring this up. It's like you need to understand why a farmer has a tendency to apply more nitrogen, and you need to provide them with better tools. So now one factor, as I mentioned before, that does have a fairly sizable impact is weather. And so there was a study that came out last year that focused on the analysis of many multi-rate nitrogen experiments in the United States, and also some from Quebec, from your part of the world. And basically what they found is that weather contributed about 2/3 of the explained variance in yield, optimum N rate, and fertilizer efficiency. So weather is a huge factor, whether you have a dry year or a wet year. And so if you ignore that, then you can not be very precise, because that's a dominant factor. So secondarily, there was soil factors that were involved, and that may be texture, organic matter content, and all that. And this particular paper also said, like, look, we need to consider risk in this whole thing. What we've found from many years of work is that basically, if you want to improve the precision of nitrogen rate prediction, given the weather impacts, you need to go to in-season nitrogen application, like the previous speaker talked about as well, because your ability to predict the optimum nitrogen rate goes up as the season progresses, because you can incorporate the impacts of the weather conditions. Now, one of the challenges that we have, and my apologies for using, again, US data, but you're not too far from where I am, is that basically that these very heavy precipitation events that are kind of driving this variability have generally increased as a result of climate change. And the northeastern part of the US, and by extension, I think where you are, has actually seen the most of that. This is the sort of the 1% precipitation events. So we are seeing more and more of these sort of untimely high heavy precipitation events that sort of drive a lot of these losses in nitrogen through leaching and denitrification. Okay, so how do we address this? So let's first review what type of recommendation approaches are out there, and I'm focusing on corn, like the previous speaker. So one of them is a yield goal approach, and it's basically typically uses a simple equation that increases the nitrogen rate depending on the yields that might be achieved. Another approach is the sort of empirical, or the maximum return to N approach. That's quite common in the US Midwest, actually the major corn states, where they basically do like what I showed you before from the data from Iowa, where they do a lot of experiments, and then they say, well, on the average, this is the optimum rate. So these tend to be highly generalized, and they often ignore important factors, especially weather. And I should say, I'm not sure, I looked up in preparation for this talk what the New Brunswick recommended nitrogen rates were, and my impression was, at least for corn silage, that it was just a single rate, 150 kilograms per hectare. So that's even simpler than this. And those are the static approaches, where basically what that means is they don't vary from year to year. They're always basically the same. The MRTN approaches are, in most cases, and for most states in the Midwest, are also a single rate for corn after corn and versus corn after soybean. So that means, like in the state of Iowa, there's one recommendation for all soils for every growing season. So it's very, very generalized. Now, in contrast, there's a so-called dynamic adaptive system. So that's basically where you, in some way, adapt to the production environment and the weather conditions. So some of them are the pre-citrus nitrate test. That's basically a spring nitrate test that gives you some predictability. Now, one of the challenges is that, sometimes you take the test and then you get a lot of rain right after that, and it's kind of useless. There's ear leaf. You can do ear leaf nitrate analysis. You can use a SPAT meter. Basically does the same thing, but it's a little measurement tool. Then you have canopy sensors like the green seeker and Optrix that basically measure the reflectance properties of the crop. And then you have models combined with weather data, which is really the area that I've been working in. So each of them has strengths and weaknesses, as you can see in this case. And I'll go into that a little bit more. So the basic yield goal-based method, which was really, most states adopted that after sort of this initial work in the 1970s. But basically, the N rate is a function of the yield and how much nitrogen is required to achieve the yield, with some credits for nitrogen that comes from the soil. That may include manure, and then efficiency factor. And so the way they've been implemented, varies a little bit from state to state, but they are, again, very static. Sometimes it's a fixed rate. As I said, this is my understanding of the New Brunswick recommended N rate, but I'm not absolutely sure that's all I could find. So that's an even more simple approach. So I'd be happy to hear any comments to the contrary. So the empirical approach, basically, like I said, is you do a lot of experiments. In this case, corn, soybean. And then you do the curve fitting, and then you determine what the economic optimum N rate is that you can see here. So it's a little different for corn after corn versus corn after soybean. The only adjustment is basically based on the prices of the corn and the fertilizer. So if the fertilizer is more expensive, then the economic optimum N rate is a little lower. Now, like I mentioned at the start of my presentation, we are now looking at more multi-objective cropping environments where we're not only thinking about optimizing yields. And with that, then we have a broader set of practices that farmers employ to grow their crops. So they may use conservation tillage practices and crop residue management. They may incorporate cover crops. They may make their rotations more diverse and try to get more perenniality into their rotations, to improve soil health. We see tremendous improvements in crop genetics, so that the yields have gone up, and so that needs to be accounted for because higher yields requires more nitrogen. There's a lot more interest in organic inputs, not only in traditional livestock-based systems like dairy. We have a lot of new equipment that allows us to do more variable timing and better placement. We have better fertilizer formulations. And then we have also more recently these efficiency additives that the previous speaker addressed, like these inhibitors, stabilizers, et cetera, that do work. But how effective that varies from year to year. But all of these practices interact with each other, and they also interact with weather. So that's just giving a simple credit for, say, a cover crop or a manure is not really very precise, because that credit is very, very, very much dependent on what the weather conditions were. And so they all interact with each other. So let's look a little bit at then the sort of static dynamic approaches. So one of the dynamic approaches is the sensing. So you can see some pictures here. This is the Yara N sensor that's mounted on the top of a tractor. Here you can see the Optrix sensor, the green seeker sensor, and this is the SPAT meter. SPAT meters are challenging from you might say from a sampling perspective, because they measure only a small part of the leaf, and then if you have a large field, then that's a lot of sampling to get a good estimate. A lot of these sensors are mounted on booms, and they can then allow for adjustments of the N rates on the go. In this case, applied through these drop tubes. Generally, you might say these work better on cereals than on corn. I haven't seen a lot of good data on corn, and I think potatoes as well, which you can see in this picture on the Yara N sensor. One could use satellite imagery to look at some of the field variability. And here is the at-farm product that's developed by Yara. One of the advantages of satellite imagery is that these satellites fly over no matter what. And so that information can be processed fairly readily. But there tends to be sort of two concerns. One is the resolution, because they tend to be about 20 meter, or in some cases 10 meter resolution, which is okay for large fields, but a problem for smaller fields. But the main concern with this technology is that is cloud interference. So you can see that if you want to look at the variability, you have a cloud, like you can see here at the top of the image, that kind of interferes with your ability to interpret. So here in this particular case, this is last year, you see that there were considerable gaps. So the satellite flies over about every 3 to 4 days. But if you happen to have some cloudy days just at the time when you want to make a nitrogen decision, that can be tough. And so sometimes you have 2 or 3 week gaps between, between images that you might find useful. So that brings us to the modeling approaches. Is where I've been spending a lot of my time and effort in the past couple of decades. So what models allow you to do is to take all these sort of these factors that impact the optimum nitrogen rate. So like, basic resources, soil type, soil health, like organic matter content, and climate, with management factors, cultivar, rotation, cover crops, tillage, irrigation. With the first 3 R's, the other 3, the source placement, timing. Then you have the weather effects, precipitation, temperature, solar radiation, and then you have the risk and prices. And so models allow you to bring all of those together, and then from that, derive an optimum recommendation. And if it's a good model, then it can bring a lot of things together that a farmer might apply on a particular field. So just to give you just a little sense of the tool here, it's basically computer-based. There's a mobile version of it. It provides recommendations and sort of a lot of background information, including graphics. Now, most of the applications now of Adapten is through integration with farm management and application software. So, a lot of consultants and farmers are now using the tool not with its own user interface, but basically linking it in with some kind of GIS-based farm management software. It can operate at different spatial scales, like zones, like you see here, or even grids on a 20 by 20 meters. It allows for day-to-day field monitoring, and this, these models can be useful for learning and fine-tuning opportunities as well. So I'll explain that a little bit more. So just to give you, it's mostly for disclosure purposes. The model was developed as part of my program at Cornell University, and we launched that in 2008. And then 5 years later, we decided that it would be better off in a more commercial environment. So we licensed it to a startup company, and in the meantime, did a lot of on-farm validation. And the startup company was acquired by Yara International, which is a Norway-based crop nutrition company. I know that they're also present in Canada. And I'm also doing that in terms of disclosure, in that you understand my relationship with these companies. And this is something that my university requires me to do. So basically, what does a tool like Adapten do? It makes simulations on a daily time step with multiple soil layers, actually 50 millimeter soil layers or 5 centimeters. It simulates the water and the nitrogen dynamics in the soil, and it uses weather data for that. It simulates corn growth, so it has a plant growth model. The soil and crop models interact with each other on a daily basis. And then from that, it estimates the supplemental nitrogen needs, including this sort of economic and risk information. And then there's all this sort of support information that comes with that. So what factors does Adapten include in making a recommendation? So one of them is the weather information, precipitation, temperature, solar radiation. Then we have extensive soil databases that include texture, soil type, slope, rooting depth, organic matter content, any previous applications of fertilizer, and previous applications of manure, by the way, with some level of detail. the cultivar, the silage, grain, sweet corn, planting date, maturity class, population and expected yield, tillage practices, a whole bunch of rotations that are being covered. We have cover crops and the credits we get from that. So I'll explain that. Irrigation, and then these prices and profit risks. So one thing to point out is that good weather data is really essential because during the summertime in our part of the world, we get a highly variable rainfall situation. So this is actually from a while ago in Iowa, but I just wanted to point out that this is area here that received a lot of rain on this particular day, over 6 inches. So that's quite a lot of rain. But you can be maybe 5-10 miles in a different direction, and you may only got maybe 1.5 or 2 inches of rain. So having really good high resolution weather data, especially for precipitation, is really critical. And so we're using that in our software. As I mentioned, there's different spatial scales. So you can do it on a field by field basis, called a point based. You can do it based on soil type or some other variability, or you can do it grid based. And so grid based is 60 by 60 feet or 20 by 20 meters. And oftentimes the input that's varied is the organic matter content and the yield potential. Those are often the factors that people use to base, to decide on grid-based applications. Outputs here, you can see, so some of it is numerical and some of it is graphical. So you can see the end recommendation, and then basically a lot of sort of support information that allows you to interpret the recommendation. And a lot of more advanced consultants and farmers find that information really useful in terms of helping them make decisions or making adaptations. The graphical inputs, you can see some of the estimated losses, both in terms of leaching and gaseous losses, how much inorganic N is in the soil, the weather information, growing degree days, and crop stage development. So those are all sort of important support information that helps make decisions. So how well does a tool like this work? So here you can see the results from a set of on-farm experiments that we did. Actually, we've done a lot of those, well over 100, where we compared the adapt-N rate with the conventional grower practice. So basically, we went to a farm and we divided a field into strips where 2 rates were applied, so the conventional and the adapt-N rate. So I like to kind of refer to that as sort of like a boxing match, because you have a winner and a loser, and there's otherwise, there's no way to obfuscate the results. So in general, when you do that and you look at the differences in nitrogen rate, so on the left side here, anything on the left part is basically where adapt-N recommended less nitrogen than what the grower was using. And then on the right side, we have some cases where adapt-N recommended more. These tended to be wet years. But so in 83% of the cases, adapt-N recommended less, and 17% of the cases it recommended more. But what's most notable is that when it recommended less, there was basically no yield loss associated with that. When it recommended more, it was justified by higher yields. It was needed. So there was actually, a considerable profit gain that was associated with that. But again, in most cases, we were able to reduce the nitrogen rate. So what are the environmental consequences of that? So basically, if you look at the leaching losses on the left and the gaseous losses on the right, so this is mostly sort of the climate related stuff, that we see, because in most cases, we recommended less nitrogen, then when we estimated with the model what the leaching losses would be, most of these were above the 1-to-1 line. That means that adapt-N leaching losses were less on the average than from the grower. And that reduction was about 15 kilograms per hectare, or about a 36% reduction in simulated leaching losses. For the gaseous losses, basically the numbers are very similar. about 39% reduction in gaseous losses. So, and it's what's important to keep in mind here is that we didn't vary anything else. We only varied the rate as it was based on basically more precise prediction of the optimum end rate. And by the way, again, going back to my earlier comment, if this were Boeing or Airbus or Bombardier for that matter, and they were able to say we can reduce our greenhouse gas impact by 39%, that would be a big deal. And so the potential is there. It's a win-win opportunity. So how good is Adapt-N compared to the optimum end rate? That's really, if it's, the closer it is to this one-to-one line, the better it is. And it's really doing quite well. The average end rate was very close to the optimum end rate. That actually, we've kind of made some tweaks to improve that. And the overall variability was, it was pretty good. It was actually very good. So you'd be hard pressed to find anything better. So the models work. I mean, you can make them work. So just to reinforce these results, we actually went back to the sites where we did some of the original calibration of the model, which was at the Willsboro Research Farm, which is just south of Plattsburgh, which in turn is just south of Montreal. It's actually probably not that far from you. And we see that for these different soil types, a clay loam and a loamy sand, that when we compare the standard recommendation with the Adapt-N recommendation, we have these similar reductions in leaching losses. So we feel pretty confident about our estimates in terms of the benefits from an environmental perspective of using a tool like Adapt-N. Now, we were actually fortunate to that some folks at the University of Nebraska, they have a very elaborate and quite impressive on-farm trial network. And they wanted to test Adapt-N. And you can see the recommendations on this field here. And they made a comparison of Adapt-N compared to one of those canopy sensors and what the grower was using. So these are the differences in total end rate. So Adapt-N recommended quite a bit less, about 45 pounds per acre less than the canopy sensor, and it was quite a bit less than the grower as well. How did that turn out with yields? Well, it was basically no yield effect. So the nutrient use efficiency of Adapt-N, a lower number is better in this case, was quite a lot better. And this is one of the real challenges, again, because of the risk factor, is it's easy to recommend more nitrogen. It's very difficult to recommend less nitrogen to a farmer because of this risk factor. So we felt pretty good about these results, and this is just this from last year. So kind of coming back a little bit to, the importance of, when we have multi-objective production environments, that when we bring these sustainable practices that we want to promote for soil health, water quality, et cetera, reasons, then it's important that we bring those together into a system that accounts for the benefits. In this case, with Adapt-N also sort of gives you the actual metrics on what those benefits are. Now, there's a lot of interest in cover crops, as you know, and I just wanted to sort of highlight that a little bit because we put quite a bit of effort into a cover crop module. And so we recognize basically two types of cover crops and then different mixtures of them. So grass and legume, and a mix that's mostly grass, a mix that's mostly legume, and about 50-50. Then we recognize different stages of termination. As you can see here, tillering or early vegetative, stem elongation, mid-vegetation. So the grasses are the first ones, and the legumes the second one. Boot head first about flower, and then anthesis. And so, of course, that is an indication of how much biomass you can expect to have. And then also we have something on stands. We have on the calendar date for termination, and how much incorporation happened. So we're really, we want to have a tool that sort of allows farmers to take advantage of, the nitrogen credits that would come from a cover crop. If they're investing the time and money to do that, then, they want that payback. And by the way, I should say, because especially the previous speaker, since we do have a module that accounts for enhanced efficiency products like stabilizers and all that, that's also an important feature in that in many cases, you can reduce your nitrogen rate if you use one of these products. They're mostly promoted for yield insurance, but they actually, because they work pretty effectively in most situations, you can actually also use them to reduce your N rate. And as was mentioned before, that then also reduces your environmental impact. So where are we going from here? So one of the things that I'm interested in is to actually go back and see whether we can link these models with the sensors. And one project that one of my PhD students, who's actually finishing next month, focuses on the lower canopy. Most of the sensing using satellites, drones, or airplanes focuses on the above canopy perspective. But as you know, especially with corn, it shows its nitrogen deficiency first and foremost in the lower part of the canopy because it favors the upper leaves that receive the light. So we're actually finding that there's quite a bit of field variability that can be managed by doing the sensing and combining that with the model. So this is still an active research effort, but I think it's really quite promising. So some summary points then. Dynamic simulation models for N management enable better precision and can better balance that producer and social risks because of the you've taken out some of that unknown factor. It enables nitrogen management in increasingly complex multi-objective production environments where we're not only concerned about yield. May result in significant environmental benefits while protecting producer returns, can provide valuable management insights, and maybe good to kind of highlight that. For example, we saw sometimes farmers who were really very adamant about putting all the nitrogen up front and sometimes doing deep placement and all that. And when we showed them the impacts of in-season management, and we could put some metrics to that, they often saw the light and saw the opportunities for change. And it's the same, with fall versus in-season applications and things like that. You can, by showing the numbers and being able to run simulations for multiple years, you can demonstrate what the benefits are of changing management practices. So nowadays, what's important, if any software that you develop, it's important that it can be integrated into other software products, because farmers don't want to have to enter the same information more than once, or consultants for that matter. So integration either with other software or maybe in the future with sensor-based technologies, I think is a very important component. That's how digital agronomy will really move forward. And I think, finally, maybe there needs to be a recognition of these type of tools in official nutrient management standards. And even in the United States, we're having a lot of challenges because a lot of these nutrient management recommendations are very outdated, and we do have good tools that are available, but often in the commercial space, and they don't necessarily get the attention. And so I'm not sure what the situation in Canada is, but there's a lot of opportunities through more of these public-private partnerships. So with that, I think actually I'm right on time, so I'm gonna hand it back. Let's see. Stop sharing.
That was fantastic, Harold. And you've hit the nail right on the head for Atlantic Canada. Most of our nitrogen recommendations are static and not at all yield-based or soil type-based or crop rotation-based. So it's a dream to get to where you're talking. I'm actually going to invite our panelists to come on up, and then we'll just direct all questions to the panelists. So Yeukai, if you want to turn your camera back on. And we also are going to be joined with Caitlin McCavour, who is Perennia soil specialist. So quick introduction to Caitlin for those of you who do not know her yet. She has a BSc in agriculture from Dalhousie University and majored in environmental science. She just recently completed her MSc at Dal in earth and environmental science. And Caitlin has been the soil specialist with Perennia for about 1.5 years now, and is a resource to Nova Scotia producers on all soil-related questions. So she's going to see if she can provide a bit of regional context if necessary. And thank you so much for joining us, Caitlin. So a question came in while you were speaking, Harold. And so Keith is asking, he says, I can see how the certainty of nitrogen requirements increases through the growth of the crop, but how does the risk of missing the time of maximum N uptake by the crop vary throughout the season?
Yeah, I mean, good question, Keith. Thanks for joining. So I think what it comes down to is that you need to have multiple applications in the growing season. So to have a starter rate, and then have something in the sort of late spring, depending on the equipment, and when you have the clearance, that is maybe a conservative end rate, based on a tool like Adaptan. And then you may, because you want to make sure that as you enter the rapid growth phase, that the nitrogen is available. And then there may be, I think there's a lot of potential for the high clearance equipment to then maybe do, a final application. That's why I'm interested in the under canopy sensing. We're seeing that the newer genotypes, the newer hybrids, tend to take up more nitrogen later in the season. So there is an opportunity to do some fine tuning. But you're absolutely right, Keith, that you want to make sure that you don't wait too long with applying that nitrogen. There's a little bit of buffer there, but you don't want to go too far, and want to make sure that you do it on time. Now, one of the good things is, once the crop is really starting to grow, like I'm still talking about corn, you have less impact of or less potential for nitrogen losses, because the evaporation and transpiration rate of the crop really goes up. So you're much less likely to have sort of these saturated soil conditions, even if you get quite a bit of rain. Most of the risk of losses is sort of in let's say the first 6 to 8 weeks of the crop, and then after that risk of losses really diminishes. The risk that then becomes a problem is that if you have a dry year, you may not reach that full yield potential. And I know some of the equipment companies, I think, are starting to get interested in equipment that allows you to do more in-field management, either with high clearance equipment or maybe with these smaller kind of robotic units that may be able to drive between corn rows and sort of apply smaller rates of nitrogen, depending, and adjusting for the weather conditions. I hope that makes sense.
That does, and it actually teased me up for a question that I had while you were presenting. So you said that as part of the Adaptan process, some of the data that's inputted is the cultivar and the relative maturity. So my assumption would be that not all corn cultivars are in there, and certainly not some of our shorter season cultivars that we use in Atlantic Canada. Do all cultivars have to be part of the system for you to get a yield-based estimate for nitrogen?
Yeah, so I don't know the exact numbers, but because you're not that different than Northern New York, so we do have some short season cultivars in there. So I'm sure we would be getting very close. It's actually one of the factors that is not that critical. So when you think about models and inputs, there's certain inputs that are really critical. But the cultivar, if you're off, if you're selecting, say, 90-day corn, and you actually have 86-day corn or something like that, that wouldn't really have a big impact. There are some other factors that are more important, but yeah. So I don't think that there would be, and there is a Canadian version. Adaptan is available in Canada. So it has been basically, and we've done some calibration work. Not as much in the Atlantic provinces, but more in Ontario.
Fantastic. And does that use like a soils database for Canada to do that?
Yeah. So we're using the Canadian soils information, and and that's been kind of processed for the use. So we kind of created our sort of a second generation soil database, you might say. Directly importing soil survey data, certainly for the U.S. that was the case, is risky because there are errors in the data. Like you can't always, like, out of a public database and then assume that all the data are correct. So we kind of had to do a certain amount of data cleaning and all that. But yes, there are the Canadian soils are in the AdaptN system. Yes, they are.
Cool. I had another question that came in about lime. So lime increases carbon dioxide emissions in the year of application, but would the net benefit from improved nitrogen efficiency in subsequent years of a, say, 3 or 4 year rotation? Would you expect to see reduced greenhouse gas emissions?
Yeah. That's an interesting question. I've never really had that question before. Yeah, I think I think when it comes to soil health, nitrogen, water quality, all of those, it's basically, if you're growing a crop, then optimizing the yield and optimizing the nitrogen use efficiency is going to have a big impact. So, and that's the good news, right? It's really a win-win opportunity. We see that with soil health, for example. We see that a strong correlation between biomass production and biomass cycling and soil health. So if you're growing a crop and you're not adequately fertilizing that crop and you're losing 20% yield, that's also going to have a negative impact on soil health, and of course you're capturing less carbon. So yes, you may be with liming, you're losing some carbon, but you're also increasing nitrogen use efficiency, you're increasing carbon capture through photosynthesis and all that. And I don't know how the exact numbers would kind of work out. I have never done the math, but there's definitely, I would think that would be still a positive outcome for sure.
That's great.
And keep in mind, maybe just to add on, keep in mind that the nitrous oxide that multiply times 295, it doesn't take a lot of nitrogen to be lost as nitrous oxide for that to have a very significant impact.
That's great. Galen, I saw you unmuted there. Do you want to add to that?
Yeah, I mean, I don't have a whole lot to add after that answer. It kind of covered a lot of it, but I think just one of the reasons why that question comes up in this region is because pH is a very large concern for this area. And so liming is often used. And so you're going to have an increase, hopefully an increase in microbial respiration after the lime is applied, as well as the dissolution of lime can actually release some CO2. So yeah, just to kind of reiterate what Harold said, the hope is that through the improvement in increasing pH and improving your microbial community and increasing your nitrifying bacteria, then hopefully you're increasing that nutrient use efficiency enough of nitrogen that it's offsetting that release of carbon.
That's great. Thank you. Yeukai, anything else to add to that?
Not really. I think they have covered everything that I would have added. Yeah.
I had another question coming here. It says, when does greenhouse gases released from equipment doing multiple applications of fertilizer have a greater environmental impact than the nitrogen loss itself?
Can you repeat that?
So when does greenhouse gases released from equipment, so like going over the field multiple times to do split applications, would that have more carbon dioxide emissions than you might save from nitrous oxide emissions by that increased efficiency, I guess, to the panel at large?
Well, I'll start with that. The nitrogen application equipment it doesn't take all that much. It's not necessarily, you can cover a lot of hectares, acres, with very wide booms and all that. So it doesn't necessarily require that much fuel to, unless like plowing or something like that. So, and again, because of that 296 multiplication factor, and what we know is the impact of, even modest amount of nitrous oxide, I'm pretty confident that that's a very minor, that, that the increased fuel consumption and the carbon dioxide associated with that would be paled by the benefits in terms of nitrous oxide reductions.
I agree. That makes sense to me too. If folks have other questions, please put them in the chat, and panelists, if you have questions for each other, also please do not hesitate to ask them.
Yeah, I just wanted to add something to that. Just keeping in mind that, all of these other factors that come into play when you're making decisions, such as, when are you going in to do those multiple applications? So that will affect the rate of nitrous oxide emissions at that particular time. So there are all those other factors, I think, that come into play. So I don't know if we can broadly say we could have said or we couldn't, but I think it depends on what else is happening in that system, I think, at that particular time.
Great, thank you. Folks, other questions? Or questions for each other?
I do have a couple questions, but I do just have a comment just for the people that are here in this region, like the AdaptN, even if it's not necessarily available specific to this region, a lot of the concepts we can really use, especially now with our increased network of weather stations in Nova Scotia, and also just kind of getting to know your soils a little bit better is always something I encourage. And even if we don't have that system that gives you a specific value yet, you can take some of that information to account into reducing nitrogen rates on your fields.
I had one point of discussion because this is something I'm thinking about. It's from the data that I presented. So for our canola, we found an NUE of, what was that crazy value? Let me just pull it up here. And from what I've been reading, it means there's potential soil mining that's happening there. And I think it's true because our control, which didn't have any fertilizer, took, like, the uptake from the control was 77 kilograms of nitrogen per hectare. And then the split application had what's this percentage? Sorry, I'm just gonna put it, yeah. So the split application had 92% uptake. This is just the recovery efficiency, which means 92 kilograms of nitrogen in addition to the 77 kilograms. We had only applied 100 kilograms to this canola. And it only happened to this one treatment. So it's something that I don't know if anyone has any thoughts on that based on either what I've presented or what you know.
I've found something similar in my master's research, Yeukai, is that you'd get about 50 to 60 pounds of nitrogen per acre in a zero control plot. And so kind of a ballpark figure that I often think about is 15 to 20 pounds of nitrogen per 1% organic matter. Harold, I don't know. Honestly, I might have stolen that figure from Building Soils for Better Crops.
Yeah, and it depends a little bit. It's an interesting issue. So one thing that, a point that I try to make is not applying enough nitrogen benefits nobody, right? It's just, you just lose yield. And applying excess nitrogen does not address the issue of the nitrogen mining. The nitrogen mining is really an issue in terms of how much carbon and nitrogen do you return to the soil. So that can be crop residue, or it can be through manure, compost, or rotations. And sometimes there's a little bit of confusion around that. but applying more nitrogen than the crop takes up doesn't necessarily benefit the soil. It needs to be done in combination with carbon, right? I mean, it's if we want to increase the carbon in soil, yes, it needs more nitrogen, but applying it as fertilizer nitrogen is not going to benefit you. It has to be applied in an organic form of nitrogen. And so that's sometimes where there's a little bit of confusion around that particular issue. From my perspective, and we can maybe not everybody agrees with that, it still comes down to providing the correct, whatever that number is, the correct amount of nitrogen that feeds the plant so it comes to its full yield potential, but not in excess. Now that's a number that Adaptan is trying to get to, and there's some issues around the end use efficiency and all that. But that's still, in general, I think the correct message. Try to get that number as correct as or as close to it as possible, and get the nitrogen into the crop so that it's also combined with carbon, and that you get also as much of that possibly back into the crop and soil system, so that you don't. The mining is a concern, but it has to be done in the context of the carbon. It's the combination of the two that's valuable. Otherwise, you just lose it if you just put nitrogen into the soil in synthetic form. You just lose it, right? It leaches or denitrifies.
Yeah, that's totally true. Yeah. So Dave Burton just made a comment in the chat, and he says one of the other issues within our region is that we have relatively few current nitrogen response trials. This is also a limitation of the effective use of tools like Adaptan in our region. We need to generate more of this data to allow calibration of these tools. Harold, when you were figuring out like nitrogen response curves, were you doing a lot of end response trials?
Yeah, so we did. I mean, just to give you a little bit of the sequence. So the initial development of the model was a purely modeling effort. Then we did a lot of detailed lysimeter studies, and that allowed us to really calibrate the different rate coefficients, like the mineralization rates and the denitrification rate and the leaching efficiency and all of those kind of things. And so we did that, and we validated that research. It's all published, and then we went on to commercial farms. And so in the Northeast US, in the Midwest US, and that allowed us to basically evaluate, well, how well does it do? And that's some of the data that I presented. It also allowed us to make some small tweaks, they're ultimately, parameters, right? So they're like dials, you might say. And so it allows you to tweak it. And what we found is that the processes are universal. Whether you're in New York or New Brunswick or Louisiana or Iowa and so what we found is that it generally, because it's a more universal approach, that it does work well in other locations. Now you do need to test it and you need to validate that. But I would say, since most of our work was done in New York, and actually in the northeastern part of New York, that's not that far from where you are, I would say that it would do well in New Brunswick. You want to test it, and like what Caitlin said, you might use some of the ideas of Adaptan and weather adaptation as well. But yeah, I'm confident that a tool that accounts for weather information and that has and accounts for these management practices would do well in the Atlantic provinces, so it's worth considering, but there aren't too many other tools out there that are model based at this point in time, but you could, at least think about. I'm in a difficult position because I work with the company. I'm not a salesperson, but this approach is promising. Whether you use Adaptan or not.
Fantastic. Well, thank you very much, Harold and Yeukai, for your presentations, and Caitlin for joining us on the panel.